I mentioned that we're going to start at 3:40, but it took less than I expected, so 9 minutes extra. I'm going to tell you what's going to happen next. So you're going to have a quiz the next week, today, whenever it's going to be. So, and it's going to be on focused on association, composition, and aggregation, but it will be on everything else from the beginning of the semester till now, but that's going to be the focus. So what I'm going to do, when I explain what those things are, then you'll know what I mean. What I'm going to do, I'm going to ask you, give you class samples, and I'm going to say farm and an animal. Now create an association for me out of that. So you have to do it using these methods. Okay, so I'm going to tell you an animal can do this, a farm can do that. Now create an association for me. Okay, so that's that. And decline the call. There we go. Yeah. So so that's going to be the quiz. The assignment, please somebody ping me so I can get the assignment and set the due date for you. Assignment 1 is out, 2 is out too. So and the other class, they were asking what do we have throughout the semester. So throughout the semester, essentially you have 2 quizzes before the midterm, 2 assignments before the midterm, and then you have 2 quizzes after midterm, and 2 assignments, and 1 final over there, 1 midterm over here. In my class, you only have concept questions for the midterm. And if everybody's going to be okay with it, and if we have time, I'm going to separate the 2 tests, which means I'm going to have you one day do the concept, only multiple choice and short answers and walkthroughs, and another day you have programming. I'm not going to extend the questions. So the amount that you're supposed to write in an hour and 40 minutes, you're going to do it in 2 hours and 30 minutes and something like that. So you have more time to program. That's the reason. I want you to write whatever comes out of your brain instead of rushing and doing something that I have. So that's going to be that. And now we have 7 minutes to go. I should have said 3:10. Anyways, we'll wait. Yeah, again, the reason that I explained to my friends over here as the other class lost its lecture on Monday. So that's why I started at 1:30 sharp and I went all the way to 3:15 to cover everything for them so they don't fall behind. And that's why I said I'm going to come 20 minutes late, because from that class to this class, carrying stuff takes time. So you're going to have half of 3/4 of the lecture today, a little bit during the lab that you're coming to. Sadly, I can't start because I said I start at 3:40. So I'm going to pause the recording over here and we'll wait for 5 minutes. If you have any question, I'm all yours. Yes, for that, yes. I always Okay, so regarding the assignment, you will submit it from anywhere. But giving everybody a heads up, all the assignments are going to get passed through a program and it's going to be tested compared to all the sections at Seneca, last semester and current semester. So if you are copying from somebody, don't. Giving you a heads up, okay? Last semester we did that and like we ran it and it was a massacre, so we don't want that to happen again, okay? All right. So today we are going to, essentially this week, we are going to talk about inclusion polymorphism, parametric polymorphism. We're going to talk about relationships, and that's it. That's the whole thing. Starting from inclusion polymorphism, do you remember what it was, inclusion? Like, do you remember the polymorphism at all? Like, what was like we had two major ones, ad hoc and, anyone remembers? Ad hoc and universal, but ad hoc was two things. One was coercion, the other one was overloading, right? And then we had, for the universal, we had inclusion and we had parametric. Coercion is essentially casting, which means because different things automatically get casted, it looks polymorphic, but it's not polymorphic. Ad hoc is the one that I call fake polymorphism, which when you look at it closely, it's not really polymorphism. They're just tricking you. So that's coercion, casting. Overloading was when you are creating a function, different signatures. It looks like it's polymorphic, but again, it simply is, they're just attaching the type names to the name. So the names are really different. So that, I don't know, load that you had with an integer and load had with an integer and a character, one is load int, the other one is load int char. So the names are different. So it looks polymorphic, but it's not. Inclusion, however, was actual polymorphism. Yeah, brings us to shapes. That is actually coming from your notes, okay? So, well, class diagram is supposed to be in resource files. There we go. So essentially, we have three classes in here, but shape can be shape of anything, right? So this is what you had in your notes, and just brought it over here to give you an idea of how it works, to kind of give you a closer look of inclusion polymorphism and how we're going to use it in future, with a little bit more salt and pepper added to it. It's the same thing that we talked about last time. So first we have an interface. Anybody remembers what an interface was? Should I pass the talking sticks, or are you going to? Yes, so essentially in C++ terms, an interface is a class that has only pure virtual functions and it has no state. There is nothing in it. In object orientation, an interface means an idea. That's it. It's only an idea. It cannot materialize. Something that you cannot materialize. C++'s point of view, abstract base class, interface, potatoes. Doesn't make any difference. In object orientation methodology, that's where interface becomes something that has its own meaning. So that shape is an interface. A shape can tell you what is its area. A shape can display itself. You can compare one shape to another. Clone, not necessarily a shape property, but it's something that we need to do when we have actually inherited stuff like this. You need classes to be able to clone themselves. What is a clone? Clone essentially keeps you, clone makes it possible for an object to create a clone of itself and return it, a dynamic clone of itself. And then you'll be responsible, if you are using raw pointers, you'll be responsible to destroy that clone. If you use smart pointers, we're going to learn later on, you don't need even to do that. The pointer is going to delete it by itself automatically. And the destructor, essentially a destructor inside an abstract base class, guarantees there is no memory leak when you are deleting any dynamic object that is pointed or referred to by its parent's pointer when it's being deleted. When you create a child in a parent's pointer, if you delete the parent, only the parent side gets deleted, not the child. Because of that, having a virtual destructor is mandatory in every single class that you create, without exception. Remember that, especially when you are writing code in tests and assignments, even if your class is not inherited. always add a virtual destructor that is empty. How do we do an empty destructor? This is how we do it. So essentially, if in old version of C++, this is how we did it. We essentially set an empty body. But in new version of C++, we're going to say new to default. New to default, essentially, it means any specialized procedure, like constructor, destructor that you have, if you set it to default, you're telling it to create an empty one. A shape knows what is its area. It returns it as double. A shape can be compared to another shape. Very fine. A shape can display itself. A shape can clone itself. And it can insert itself. And a shape can be inserted into OStream, in this case that we have. And that is the sole reason that we actually have a shape.cpp. Usually interfaces don't have shape.cpp, but because I added helper operations for the interface, therefore I need a CPP file to place those, not that one here, actually place those things. So essentially, I'm saying to insert is to display. We're okay with this? Problem? Question? Okay, let's now implement a square. So essentially, a square by itself is just implementing the pure virtual methods, whatever it does. It returns an area, it compares itself with a shape, it clones itself, and displays something else. Now, constructor, there's no problem with it. So when you look at the constructor, life is beautiful. We have no problem with it whatsoever. You just constructor, you set the side. So, and we're going to say a square has a side, right? That's how it's identified with. Now I'm going to say the square over here will have a side, and it sets the side to whatever that is coming in. The area is side multiplied by side. To clone itself is very simple and straightforward. Essentially, you say create a nameless square out of me. So you're essentially calling the copy constructor and and returning that dynamic thing out. And although it's a square, but because the pointer is shape, you're fine. You cannot make the pointer square over here. Then it's not an overload. That is not an override anymore. Overload is the wrong term. It's not an override anymore. To display a square, I explain in display how it's supposed to be displayed, whatever I want. Now, to compare a square to another, that's where it becomes tricky, and that's why we are actually having it in OOP345. The rest of the stuff is OOP244. There's nothing wrong with it. No problem with it. When you create base classes and you put virtual or pure virtual methods over there that handle references of the interface, in children that always becomes problematic. When I want to compare a square to a shape, how do I know it's even a square? Maybe it's a triangle, maybe it's a pentagon, maybe it's a circle, whatever it is. Because of that fact, we use dynamic cast. If you remember the constraint cast that we had in OOP244, essentially, these are casts that is like Big Brother's watching. You don't just cast it. The old cast that we had in C, we just converted, kind of forced type conversion with no type checking. Now, we are trying to make the language safer, therefore we have constraint casts. So what happens over here is this templated cast that I have tells that I want the address of shape that is coming in to be casted to a square. First of all, you cannot cast objects using dynamic cast. Dynamic cast only works on pointers. You can always tell that I'm pointing to a chair, pointing to a table, pointing to ceiling. Pointers can be casted. You cannot cast a chair to a table. That doesn't make sense. Okay? Pointing makes sense, but the object itself cannot be casted dynamically. So that's why I create a temporary pointer over here, SPTR, and I would say I want that SPTR dynamically upcasted to a square from the shape. Now, if shape is actually as a square, it will be upcasted, and now SPTR will point to a square. If it's not a square, this dynamic cast will return null. And that's the key that helps us set this thing properly. So now I can say this Boolean thing, it says, if this thing is not null, get the absolute value of the difference between the two. If it's less than a certain thing, they are equal. Why did I do this? Why didn't I just say check for equality? Yeah, why? Why can't I compare float values? It's not, first of all, float. It's real number or double. That's a double, OK? So, yeah, we should not. But why? Anyone? You don't know why we can't? Because they are. So when I say floating point, then I say double, what that double stands for. What is the long name for double? We say double what type? Double precision type. You follow? Did I lose everybody? So when you're actually having real numbers, the numbers are never precise, ever. It means if you have two exact logics that you're 100% sure that they are going to get to the value 2. If the two logics follow and the two variables that they have 2 in it, if you compare them, it may go false because the logic that you have generated 2, but that 2 is 1.999999999, and the other one is 2.0. This, from the eyes of the computer, still, to the eyes of the computer, it's unequal. It's false. But to our perception, it's right. Because of that, always get the difference of double values and make sure it's below certain precision that you have. So if it's smaller than this, it means they're the same to me. OK? Does that make sense? So now I can actually say if it's not null, now it means that it is actually pointing to something. I can see what it is. But if it is null, then I'm going to return false. It means they are not the same shape. And clone does the same thing over there. Now, having this type of thing, and I'm going to use the exact same logic to do this circle. So circle is exactly the same. It's just the property is different. This one is radius. That one is side. That one is side multiplied by side. This is radius multiplied by radius multiplied by pi. So the things are different. It's still a circle, but the way it's showed is different. The way it cloned itself, it clones a circle. And the logic behind equality is the same. So circle PTR, OK? Oh. It works the exact same way. So having something like this, now I can actually create different shapes and stuff on the fly. Now if I actually come to my main that tests this, you'll see, first of all, to display shape, I get the shape, and I'm going to say if it's null, say it's null, otherwise just show it. And because the target of shape is going to go to the insertion of a shape, automatically the proper display is chosen, therefore the display is. So essentially, we are reviewing inclusion polymorphism over here, virtuality. Are we good? Or we are in deep sleep? Are we good? Good? People at home, are we good? Yeah, somebody typed yes. All right. Now, make shape. What does make shape do? It asks the user what type of shape do you want, and it returns a shape so that the user can actually check if it's a square or a circle and gets the values based on that. It switches and dynamically creates the one. And it can put them both in the same pointer because they are inherited from the same thing. Hence the concept of inclusion. So square, the return value over here is a shape. It's either a circle based on what the user wants, and it returns that. So the test program that I've written over here, what it does, it creates two shapes and clones one of them. And then does a comparison between the two, and we can walk through this and see exactly how it works. And this one, the second one will never happen because of comparing a clone to itself. Obviously, they are the same. They can never go wrong. But this is the one that it might go wrong. So we have different types of scenarios that it might happen over here. One is that I have a square and I have a circle, and they are not the same. So the circle is showing, square is showing the square. But when I actually show that the S2 and S1 are different, they're complete two different objects. Or I can have the same object, and they're different, okay? But if they are identical, we are fine. So if I go 12 and S12 again, then they are the same, okay? With Visual C++, press F10 to start the debugging. This is the last time I'm going to mention this, so if you haven't done, just listen carefully. If you've done it, fine. Okay? F10, if you forget what F10 and F11 and shift of what F11 does, click on debug. Over here, it tells you exactly what it is. F11 steps into, F10 steps over, and this steps out. So I'm at this stage. I want to step into the make ship and see what's going on. I press F11. I go inside. In here, it creates a pointer and two values. Prompts the user, ask for the type that the user wants to enter. I'm going to say S. It comes in. Let me actually put it side by side. So it's going to switch to the type, get the length, and create a square out of the number that I want. So a new square is returned and returned out. Now, for the second one, because I know how makeshift works, I'm going to press F10 instead of F11. So essentially, it jumps over, which means it runs the whole thing as one command. It doesn't walk through inside. Now I'm going to put over here S again. Or let's put the circle. Now S1 is going to get cloned. So essentially, it clones the square and puts it in that one. This one, I'll press F11. It goes, oh, not here, F11. And it goes to the clone of the square, creates a new square, and returns it. Therefore, CL over there, the clone one, is actually a square. Displays shape 1, shape 2, a square and a circle, and shows the clone, that is a square. Now, if it compares the two, when it goes to comparison, in comparison, the SQR over here is off square, tries to cast the shape over there, which is not a square. Therefore, the outcome is null. Therefore, what it returns is false, and it says it's different. But when it actually compares a clone to itself, the dynamic cast is successful. SPTR actually points to a square, and they are identical. Okay? And deletes every single one of them, and we are done. And that's inclusion polymorphism review. Questions? Suggestions? Objections? Good? All right. So let's stop this. Maximize. Next one, parametric polymorphism, which is essentially templates. Parametric polymorphism. Yes. Let's go to here. I'm going to set that startup project. Close all. So with parametric polymorphism, again, reviewing 244 stuff, what we did was essentially doing something like this. We said when we have a function, and the function that we have a specific type of use, let's say let's say if I have something like swap, and I want to swap two values, so integer pointer A and integer pointer B. To swap the two values, I create an integer value, and I'm going to set it to target of A. And I'm going to say target of A is B. And target of B. And I'm going to say target of B is V. So that becomes a swap that I have done. Now, if this swap is handy and I want to do it for many different things, I want it to work for everything. So how do we do that? Two ways that I can do. Either I predict what I want to do and I keep changing and overloading. So if I keep overloading this and have another swap for doubles, what is the problem with this? The problem is nothing. The problem over here is that your executable is growing fatter and fatter as you do this. Why? If I can type double, of course. Sorry, it's too low. I have to do like this to be able to type double. OK. It's hard to type like this. This doesn't come up. It's an old podium. It's made for small people. So when I do this, when you compile your code, you're going to have two functions in here. If you use it or not, if I right now compile this thing, my executable will contain a swap function for two integers and swap function for two doubles. And it will stay there even if I don't call them. That's the genius of templates. The template says, I will create the executable for your function, the code for your logic, only if you use it. So how does it work? We actually tell to the compiler to replace the types with whatever we want. So I simply say template, type name T, and then replace the types with T. So what happens over here is this. The template creates the function definition on demand. What does it mean? It means when I actually call the swap, I'm going to say integer A, B, and I go swap. Because these are integer pointers, compiler understands that it needs to replace the T to whatever type it wants to. Be OK with this, right? All right. And it will do the same thing if the type was, I don't know, something like character or whatever you had. Obviously, when you create this to document this template, you have to mention what this template supports. The template is passing two addresses. Nothing important is needed over here. What I'm creating over here in this case, I'm creating an empty thing. So if I create it like this, the other one that I created, I was actually creating it and assigning it at the same time. I was initializing. This one is creating. So T over here needs to have a default constructor. Otherwise, your swap is not going to work. T must support assignment operator. Otherwise, it's not going to work. So these has to get documented. Now, if I do like this, then the story is different. The requirements changes. This is a beautiful question for a test. Now, what are the requirements? Can anybody tell me? What does T need for this to work? Only copy constructor. OK? And assignment operator afterwards. So it doesn't need default constructor. This type doesn't need to be defaulted. Got it? We good? OK. So that was the extent of OOP244. .244 func template. But now, we create a template like this. So this template of mine wants to return a copy of the largest between the two. First of all, it receives the values as copies, okay? Then it returns the copies out, which is very fine, okay? So if I run this for, say, 2 integers, it will work perfectly. So or 2 doubles, it doesn't make any difference. So I can simply do this. Largest of A and B. Obviously, it's going to create a double thingy and return it, and the largest of the two are double is going to get printed. Are we good with this? What if I have a class like this? I cannot use that with that largest thingy, right? Because it doesn't have an assignment, a greater than operator created for it. So it's not going to work with the container. I cannot find the bigger container between the two. What can I do? 2 things. Overload. You can just overload the largest to whatever you want. Remember, overload always supersedes templates. If you overload the object, so if I create a largest that returns 2 containers with whatever I want, so essentially if I create something like this, it's perfectly good. There's a problem with this, though. You just screwed up all the concept of templates that I just learned. I'm creating a template, so the executable doesn't get the logic of the function is not created in my executable if I don't use it. But this is not like that. So you can always ignore the template and convert any template to a specialization. How do you do that? To make this a specialization for template, which means if you don't use largest with a container, you don't want this overload to get created. You have to convert this to a specialized template. How do you do that? Number 1, you put a template signature at the top, but you don't mention what is it for. So it's not going to get generated for anything other than now you can actually tell it what you wanted to create it for. And that's by adding the signature to the name. So you are saying anytime a largest wants to get created for a container, generate this one. Done. And that's how it works. That's specialization. And you can specialize it with anything. Of course, it's going to have different meanings for it, but it would work, hopefully. So this one is not going to return a copy, but it's going to return the address of the largest string between the two. So if I create something like this, any constant character pointer, that's going to get returned, and therefore you're going to have the largest one. So that's essentially specialization for functions. Any function template that you have, just overload it for what you want. After overloading, put a template at the top and write over there what you want. Are we good? Are we good? So this is function template specialization. Now we can use this specialization to resolve conflicts if we want to. What I mean is that, take a look at here. Oh, We are still on swap. Give me a second. So say over here I have do I need to create, well, how can I actually make this thing work? It's not applying coercion for it, because it can't. You are actually having the largest over there, and largest, you know, it receives 2 t's. So they must be identical. When I create like this, the compiler gets confused. It doesn't know which one to cast, which one to do coercion for. For this, you can use the exact same method you used for specialization and force compiler to generate a version of the function that you like to have. Now, for this thing to work, what should I do? I think the best way is to create a largest double and pass the integer to it. So it casts the b to a 4.0, passes through and returns it, right? So to do that, I can simply say, hey, compiler, I know you're confused, but don't worry about the arguments. Just create a double version of this and call it. So like this, you're actually resolving conflicts. You can tell to the compiler which version of the function template is needed, and it's going to create it for you. Be good? Easy breezy. Resolving what? Resolving function template conflict. Okay. Enough with the kindergarten stuff. Now we're going to go to good ones, okay? And for that, we're going to take a break. So break, 10 minutes, and we'll come back. Please remind me to resume recording. So now that we actually worked on the function templates, I'm going to remember how it worked. We need to see how classes are converted to templates. We don't use only templates for recreation of logic. We can actually have entire classes converted to templates, and it kind of makes our life much easier. So let's take a look at this. This is what we have done in OOP345. So we were dealing with arrays. We were dealing with arrays in IPC 144 and OOP345, and no, they really suck. Why? Because you don't know what their size is. If you exceed the index, it's going to screw things up. If you pick certain size, you have to jump through hoops to change its size. So it's pretty difficult to work with. That's why we created this integer array thingy to use instead of an integer array that we had. So essentially, what is an array? An array is nothing, as we recall, an array is nothing but a pointer that you have, and that pointer kind of points to a piece of memory. And this piece of memory has numbers or whatever. So whatever this pointer is A over here, then A0 essentially becomes the very first element that you have, right? That's actually how it works. So we did the exact same thing over here. What we have done we said, okay, if you want an array, no problem. If you want an integer array, I create an integer pointer. I keep its size so it knows what the size is. Not only that, I'm going to make it privately resize itself if you go off boundary automatically. So you don't need to worry about that. I'll give you a construct. You can give you a constructor to create any size that you want. So you can create the size of the array that you want. I make sure it copies and assigns itself properly so I don't have any memory leak. If you want to know what is its size, you don't have to pass its size with the function to the thing as an extra argument to a function. It knows what the size is, and you can always ask what a size is. I'll make the index operator, I'll do the index operator so it works exactly like an array. If it's non-constant or constant, it doesn't matter. I'll do them both. I'm not going to be able to get there, okay? And I'll make sure I have a virtual destructor if in the future you want to do something. I also don't have a memory leak. I also added something extra to this thing that no array does, which means if you print my array, it's going to print it comma separated on the screen. Just how it's done. It's very simple and straightforward. I'll go through it. It's kind of a review of rule of three at what we had last semester. So I'm going to open this up, split it in two, and explain exactly how it works. For the construction, I simply make sure that the size is good. If the size is less than 0, I know the guy had a bad day. I'm going to say the heck with it. I'll assume it's 1. Okay? And I dynamically allocate whatever the size is. At the same time, I'm setting the size of the attribute size to the value. And I have an array of that size. They put 10 over here. I'm going to set m size to 10, and then new, and then done. Okay? So that's that. Copy constructor, copy assignment. We're not going to go through it. It's not that important at the moment. We know it works. For the destructor, I'll delete everything after it's done. Size returns what is its size. The index operator works in two different ways. If you use the object as a modifiable object that is not constant, and you pass the index the size, first of all, if it's less than 0, it says you're out of your mind. I'll give you 0, so it doesn't matter. If the index gets bigger than the size, then it resizes itself first, then it returns the element. Therefore, no matter how far you go, it makes itself bigger. No problem with going off the size of the array. But if you deal with the array as a constant, if you pass the array as a constant, obviously it cannot resize itself. Is that the case? I'll force it to loop back on itself. So if you pass the index 5 and the size is 4, it does 5 mod 4, and it makes it 1. So it always stays between 0 and 4, whatever the size is. So you can never go outside of the size of the thing. And displays it comma separated, as you see. And resize does the normal resize thing that we do in dynamic memory allocation, which is essentially allocate the new size, copy everything from the old one to the new one, make sure that I have the size of the new one, and then delete the old data, assume the new memory using the data pointer, and it's resized. So very simple and straightforward. Like this, I can use anything I want, and it's good. There's only one problem. It's only for integers, and that sucks. We don't want that. We want it to be for any type. I want to have an array of anything. Okay? So how do I do this? Number one, when you create templates, what does the compiler do? Compiler actually looks at the logic based on the type that you want. It would recreate the logic for you with the new type, right? So it needs the logic to recreate it, correct? So at the moment of compilation, it needs all the code, which means you cannot have a regular module with templates. With templates, you can't have a CPP file, because CPP files are not available at compile time. Only the header files are available. So because of this fact, it's a rule that all code, everything about a template should reside inside the header file only. Are we good with this? So to convert this thing to a template, what you need to do first is to create a header file. So the header file I want to create, I'm going to call it dynamic array, not an integer array, .h. And obviously because, I want this dynamic array to work with the standards that I had, I'm going to create the proper setting for it. Now that I have the header file, I will bring everything inside the header file. So I'll go to the dynamic array, integer array, copy everything that I have for the code, and I put it in this namespace. So that's number one. So very first thing, I'll get all the header file. Number two, I'll go for the CPP. I'll get all the stuff that I have for the CPP file, and I'll bring them in. Seriously, really? There we go. Copy and put everything right back in here. And now I'll remove the old things. I do not need the CPP, and I'm done. Do not save. Get out. I hope I copied everything properly. And I'll remove these things from the project. Remove. And add a tester over here. Add new item. That's the main thing that we're going to have. So now that I have this, I need to see how do I convert this to a template. Number one, every scope needs a template tag of its own. Okay? Every scope needs a template tag of its own, which means to each tag you have to add, to each scope you have to have add a template statement. So template. And I'm going to put over here type name T. So that has to get added to each scope. Scope number 1 ends at line 20. This one is only a one-liner, but still a scope of its own. So it needs a template of its own, even if it's only one line. OK? This scope, so every and each scope will have its own template. And finally, done? That's number one. Number two, how does the compiler know what to create? In what type to inject into that template? When you think about it, in functions, when you're actually creating a function template, compiler has the signature of your function call to detect what type should be injected. If you're saying largest integer and integer, it knows it has to create an integer largest template. If you go largest double and double, then it knows it's double. Container, container, it knows it's container. With classes, you don't know. If I look at the class, when I actually, let's say main in here, I'm going to say include. Dynamic array. Let's include IO stream. I know we're going to need it. Using namespace Seneca. Using namespace std. So if I want to create a dynamic array, seriously? How does the compiler know that I want that dynamic array A of mine, that I want it to have 10 elements, I want it to be of type double? It doesn't know. Because of this fact, all class templates are created using the same method you use when you want to resolve conflicts for the functions. If you had the largest with 2 different arguments, you want it to be double, you enforce it to be double by adding the double after the name of the function, right? You do that all the time with templates, with class templates. So if I want this dynamic array to be of the type double, I have to add double over here. And that's how the compiler knows it is supposed to be a double array of type double. Are we okay with this? Do we understand this? Now, having said that, we have to come back in our template and do the exact same thing to, oh, why this thing is int array? Dynamic array. Let's change them all. That's better. Okay, so it's dynamic array, not integer array. Okay, so now this dynamic array of mine should carry the signature because it needs to know which like in here, when I'm actually saying dynamic array constructor, which constructor? Dynamic array for double, dynamic array for container, dynamic array for integer. It doesn't know. So you must give it that signature. But that has a rule. And there are 2 rules to follow. First one is 1, and second one is 3 different steps. Number 1, when you create a template, you need to change, when you are converting a class to a template, first of all, you need to change the type, the focus type of your logic to T. If this dynamic array is now an array of integers, when it wants to be T, it should be an array of T's, right? Therefore, the types that are related to the type of the array should change. Let's take a look. So this int should be T. There is no question about it. Size is size. 5 trucks, 5 integers, 5 doubles, 5 is 5, size is size. It doesn't change. Same thing over here. Same thing over here. Same thing over here. Same thing over here. Here, this operator is returning an element of the array. Therefore, this int must be the reference of T, not int. So that has to change. And also here, that has to be T. Index is index. It has nothing to do with anything. I don't need to change the index to anything. But T has to change. The rest remains the same. It's good and nice. I should do the same thing for the other ones too. For example, in here, you see that int over here? I am creating M data. I'm going to say new array of ints. That is not supposed to be an int. That is supposed to be a T, because it's creating a new array. So you have to go through all these things, and those have to change. Like that. Or here I have nothing. Here I do. See, I'm actually creating a new one. So that has to be T. Here too. When I'm resizing, I'm creating a new T array. Done. Okay, so that's that. After that, I need to add the signature of the template to every single class name with 3 exceptions. So T should be added to every single class name with 3 exceptions. Number 1, the name of the class that comes right after template. Why? Because it's the name of the class. It's not instantiating anything. Essentially, you need the T where an object is being referred to. This is the name of the class. Doesn't happen. Number 2, name of special functions, special procedures. All constructors should be ignored because constructors are not object They are not indicating a specific object. They are telling when the object is created what to do. And also the destructor. So the class name that comes right after, constructor names, and the destructor. You don't touch them. Everything else must carry the signature. So this one doesn't. This does. This is a reference to dynamic, dynamic array. So that has to carry it. This is a constructor. This is a reference. Reference needed. This is a reference. It needs it. In here, take a look. There is anything else? No, I think it's good. Now, this single line. In here, a reference of a dynamic array is passed to be printed. It needs to know what it is. So that needs a signature. Same thing over here. It needs to know which constructor of which object. So that has to be T. Sorry, I put Control T instead of Control C. That has to be, if I can type it over here, it would be amazing. That has to be T. But the next one is the class name, is the constructor name. You don't. Here, this is the owner. It needs to be T. This is a reference. It needs to be T. The rest, it doesn't. So you go through all these things and change them all. And at the end, you're going to end up with something like this. Changing all the stuff, it's going to be, oh, this is wrong. 2 deletes. Here we go. And this is going to be the dynamic array that you end up with. So now, having created such a thing, what you need to do is just to mention what you want. If you want an array of doubles, it gives you an array of doubles. I think I have a main over here for it. Just going to bring the main. There you go. Now I have an array of containers over there. It's going to just go through it and run it perfectly. And I can actually add another one over here. So I'm going to create dynamic array of doubles. And I'm going to create only 2 of them. So this has 2 elements. And in here, I'm going to say di, although that goes up to 4. But this is I plus something like that. It's 2, but it's going to resize itself. So it's completely safe. I can actually use it. And now I can actually see out both of them. And it will actually work for both of them as 2 different arrays. There we go. Oh, wrong thing to compile. This should be the startup thing, sorry. Templates, startup project, one more time. And there we go. So the top one is containers, the bottom one is double arrays. You can have any type of array. Good news, 99.9, you don't need to create anything like that. I was mentioning it to the other class. I don't know how any of you remember that old slogan of Apple, very old one, older than you, that it used to be, it says, you want to do this, there is an app for it. You want to paint, there's an app for it. You want to order food, there's an app for it. That used to be the slogan of Apple. So you want anything, there is an app for it. At the time, people didn't know that cell phone is not a cell phone. You can actually have any type of app on it. So the same thing happens over here. Anything you want, there's a standard template library instance for it. Anything you want. You want an array? It's actually called array. You can use it. But array is inefficient. It's linear. You can use a vector. You can use a queue. You can use several different types of things. Not only that, there are algorithms. Like you want to count do process through 50 billion data and you want to done in parallel, you can actually run a standard template library, say I want to search through these things on a computer with 10 cores. It will do it for you. So everything is actually templated in C++, and that's the beauty of it. Okay? Of course, we're going to learn how to do it manually, but there's a template for it. So anything you want to do, there's a template for it. Now, when you're actually having templates, you create a template of your own for anything, make sure you document it. You go through it closely and see what are the edge cases, they call it, for your class. In here, for example, in the definition, there is nothing. I just want to see over here. So, for example, when you get to this, what do you see that the T class, the T type, should have for this thing to call, to run? Anyone? In line 34, what should T support so that line is possible? That's 345 thinking, not 244. You have to really think about it. When you create an array of something without initializing it, it means each element must be defaulted. Therefore, T must have a default constructor. That's one of the documents that you have to write. For this thing to work, for this template to work, T must support default construction. Now you come over here. As you see, when it's actually copying, you are setting one element to another element, correct? These are the elements of T. Therefore, assignment operations should work for it. So it's safe to say rule of 3 should work for the T. Okay? And things like that. So you have to go through it and see how everything works. Now, in our case, because I have that comma-separated thingy printed down here in display, I'm actually displaying each element. So type should be insertable into OString. Good? That's class templates. And after that, we're going to go to composition, association, and things like that, which we are not going to cover today because it's a huge thing to go through. Okay? Questions? Can somebody please send me a message on Teams telling me to activate the thing when I get home? The assignment submission script, so you can actually see what's the date. And again, you don't need to be anywhere. You can submit it from anywhere, okay? And one more time, all the code that you're submitting will be compared with other submissions throughout all 3, 4, 5, and BSD subjects. So be careful when you're writing your code. Questions? Suggestions? Objections? All right. I'll see you during the lab. People at home, are you awake? You have any question, anyone? No questions? All right. Have a beautiful day, everyone, and I will see you soon. Oh, one more thing before you go. I wiped everybody off the team because for some reason 2 teams were mixed. Subject E, I think, had everybody in it, and so I wiped everybody up, created everything from scratch, and submitted it again. So you are in one team now, right? You're not in the other one. Okay, good. I just wanted to make sure. Okay. I might create a joint team separately between the two so you can communicate with each other, but yeah.